Assalamu alaikum students, and first of all, sorry for the delayed video on experiment number 11A, but I expect those who are going to do 11A in this session 2021, they are the very best of the session, and they will be like just 25 or 30 in number. So I expect something very good, and just as a very important point here, I will select the top two PCBs from this experiment, whoever they are, from any other section, any section A, B, C, D, and I will personally make their PCBs myself. If they are, of course, they are something very, very short size, then we can do that, and I can do that. At least the top two, the smallest size, and of course the better, I'm going to make them, so they don't have to be at the cost. So try it that the best two PCBs they are. And of course the components but the PCB part I am going to actually make it. So this is just a small initiative for those who think actually that I'm a bit late, and I hope you can do it, because 11 a.m. I'm going to give it a deadline of approximately tomorrow, so Wednesday. So now what is this experiment? Let me just talk a little bit. The diagram is with you. I guess it has been shared with you from the CRs. If you see the title of this experiment, this is very, very important thing, and I told you that once you make this thing, this can be, you can place it at your home and you can have anything changed over there, and you can control 5 devices, and 5 devices, 5 nodes over here. The word node over here, as you can see, the 5 node control. By node over here I means a device, and it's an SMD PCB. There is no condition that you have to make it 2 layer, but if you are going to make it a single layer PCB, then of course the size is going to be a little large. But so I'm not putting a restriction that it's going to be a 2 layer or whatever. So you can make it a single layer if you think, but remember, then everything has to be on the bottom layer. Then it will be a little bit large size, and all the components are going to be. Now, as this is an Internet of Things over there, and this Internet of Things are going to control a 5-volt relay, and the relay number or the name is HK4100F. The reason of selecting this relay is this: it's a very small relay, and it can easily handle 1 ampere or maybe 2 amperes of load easily. And by 1 ampere and 2 ampere means that the current it can actually turn on and turn off. And by relay over here, I actually mean a device which can actually turn on or turn off a device that is going to be running at supposedly 230 volts AC. That is actually the national grid voltage in Pakistan, that is 230 volts. So when I'm talking about the word relay, this relay means that I am actually going to have a simple coil like this, and this coil in my case or for this relay is actually 5-volt actuated. And by coil actually I mean that it's actually an inductor, and we all know that whenever there is an inductor and I am going to apply some, like supposedly 5 volts over there, then because of that 5 volt I will have 3 pins extra on this one. And by 3 pins, supposedly this is the first pin where I am going to give this is the first pin over here. I am going to apply the voltage. This is the second pin from where the current is actually going to go out. So the current in the 5-volt inductor is going to be moving like this, and when it will be turned on, which means that the relay is going to have this current flowing over there. So what will actually happen, that your relay, there will be a movable contact, and that movable contact initially that was at this point, and then it will move on because there is certainly going to be a force of attraction over there. So this movable contact over here, this will be moving over here. So what will happen actually over there, if I make the complete diagram, supposedly this was your circuitry, and this circuitry was being powered. Supposedly there was an AC source over there, and AC source, I hope you remember from your circuit analysis that this can be device over here, and this is connected with the live over here, and certainly this is the neutral over there, and there is a device. Supposedly there is a motor. Now I am representing a fan or a motor by this symbol. So when I'm having a fan or a motor by this symbol over there, so the neutral is already connected to the motor one, and this one is approximately the 230 volts over there. So now when this contact will be connected, I'm just going to try to actually make this line a bit better. So when this will be connected over here, and this will be connected over here. So now if I am going to supply a signal over here, and supposingly, let me just make this a 5 volt relay, and for that 5 volt, supposingly I have a 5 volt supply over here. In fact, I have to make it full switch. So this is positive and negative, and this is my 5 volt. So now I connect my 5 volt over here. This is that ground over there. Remember, this ground over here is totally different from this ground. This is the AC ground and this is the 5 volt ground. So remember, they are not the same ground, and I have indicated that one in the picture as well. So now when this relay is going to be used over there, so what I am going to actually do it over there, this relay is going to be actuated by a simple transistor, and that transistor over here is going to be that 2n3904, and then this is going to be grounded. And let me just check it on the waveform over there. In fact, this is a little different from the one which I am actually putting it in you. Let me just change it. It's actually a different configuration. So this is my 5 volt connected over there, and on the other end of this one I am going to have a transistor, and that transistor is the same which I am talking about here. This is that 2n3904, and there is that 1K resistor. And I hope you are familiar with this all 1K and 2n3904. So now what is happening, that when this transistor is going to be turned on, which means you are certainly going to give some 5 volt or 3.3 volt signal. I will come back to it at a little later stage. So what will happen, this will be base emitter will be turned on, a current will start to flow from this and this one. So what will happen, the fulcrum which was initially at this point, it will move over there, and now this will be in contact. So when this will be in contact, this means that the 230 volt will be traveling from here to here into the motor, through the motor, and coming out, because the neutral was already connected. Now this neutral is the same thing as the black color wire in your home circuitry, because in your homes, if you open any of your power circuitry, that is that black color which is normally used by the electrician as the thandi tar, you call it, or the live wire, or the hot wire, you call it. So this is that circuit. Now what is happening over there, this point over there which you have just seen over there, this is the common point for the fulcrum, which means that this point remains connected to the live end of your device, which means that this is going to be the common point. So this is already called as common, or simply C. And this point, because when the relay is not energized, which means the inductor is not having any magnetic pull, or it's not having any electromagnetic pull, it's not behaving as a solenoid, this is actually the normally open point, and NO is actually the abbreviation used for it. And then if you have this closed, which means that the circuit is operating, then this pin is called as the normally closed point. So this means that relay is actually defined by 3 or 4 points. The one point is the entering point of the coil, the other is the leaving point of the coil, and then there are 3 other contacts which are actually being used over there. Now whenever you are going to have this transistor turned on, and certainly this means that this circuitry on this side is operating from 5 volts and 3.3 volt in our case, and this circuitry is totally isolated from the other, and we really need it, because 230 volt is a very dangerous voltage. We don't want our microcontroller or our circuitry to be having any connection, and for this purpose our relay over here, this is that relay which I am talking about, is the perfect case or perfect addition to this circuitry, and this is actually producing that. So our circuitry is going to be similar like this over there. The only point which is very important over there, that in this case you are actually going to make, let me just make it, so you are actually only going to make, if I can make a small box over there, this is my box over there, in fact like this is my this one and this one. So practically this shaded region which I have just made it over there, this one you are actually going to make. This point normally closed will be actually connected over there, over on this one over there, and then let me just confirm on this one. This is the normally open. In fact, I have just made a little problematic. Please correct this one. This is that normally closed, and this is that normally open over there. Okay, now when you have made this, you have this shaded region. You have to now you are going to have 5 transistors like this. Now in this circuitry, if you are not giving any signal to this transistor, this will never be turned on. But you remember, any circuitry, if you just touch the pin of this one, the transistor can be turned on. So in this one, you are going to attach one change case over there, and if you see your circuit diagram over there, I have added a 10K resistor over there, and this is a bleeder resistor, and this 10K resistor is going to be added over here like this. Again, an sMD version 1206 is enough, and this resistor is actually going to take care that if by chance any stray voltage is available at this pin, you are actually not going to turn it on by mistake. So you need definitely 5.5 volt, or sorry, actually 5 volt or 3.3 volt for this to be working over there. So this is that structure which we are actually going to do it, and we need a 5 volt signal over here, and that 5 volt is going to be produced by a converter shown over here in this one, and then you have this relay. Now one just addition over there. Now you have gone through your circuit analysis course. Whenever an inductor is going to have a current flow through them, certainly it's going to be like this, and you are actually going to turn off this transistor. The problem would be that when this transistor turns on, or it's going to turn off, the inductor is going to have very high spike of voltage, which is LdI by dt, if you have gone through the circuit analysis course up till now. So this is going to produce a very high voltage spike, and because of that spike, this transistor cannot sustain it, and it can actually damage itself. So there is one case that you are actually going to put a small diode over here, and this diode is going to work because when you have turned off this one, the current was still flowing through the inductor, so it will try to dissipate its energy through that inductor and does not make, because if you remember in your transistor, in your L over there, whenever there was an inductor inside any circuit, that inductor was always going to produce a high voltage, that is LdI by dt, and that was actually I, because when you are going to turn off, there is going to be a current change in the inductor, so there is going to be a voltage spike. This inductor in our case is that same 1N4148 over there. So this is that diode over there. So now what this means, that you are actually going to make this all circuitry, this all over here, this circuitry is going to be added approximately 5 times over here. This is very, very important because you are having 5 nodes over there. Now coming back to your circuit diagram, this is the same circuitry if you have just seen over there. This is the normally open, this is the normally closed over there, and now since you are going to have 5 devices being controlled, so you are going to have 1, 2, 3, 4, 5 points over there. These 5 points are going to be the point at which you are going to control your devices, and these 5 points are actually going to be, let me just change the color on this one. These 5 points are going to be connected to this normally open pin of the first relay. This one will also be connected to another, that is actually of course the second relay. This one will be connected to the third one, this will be connected to the fourth one, and this one would be connected to the fifth relay. So in short, you are actually going to repeat this circuitry, which is actually this portion over here. This portion is going to be repeated 5 times because there are 5 nodes over there. Now the interesting thing that you are going to give 5 volts to this circuitry because you have a 5 volt signal given to the relay coil. That 5 volt is going to be available from a converter. Now when I'm talking about the converter, since this total PCB has to go inside the main box over there, that is inside your homes, so that 5 volts is going to be produced by a small power module which is named as HLK5M05. Now there are 2 versions available. Now let me talk on those 2 versions over there, which is very, very important. The 2 versions, if I can show you over here, the 2 versions available, and I have given you the footprints in the zip file arranged to you. This footprint, as you can see, it's a very small box. Let me show you the box first actually. The box is something like this I'm talking about. This is the box, and you can see this is the AC terminals, of course, at the bottom over there, and this is the negative and the positive output. Don't need to add any capacitor, any something, just maybe a capacitor just for any filtering purposes if you need a very good filtering point. Otherwise, you just need a capacitor output and this works fine. And this is a very small package. You are directly converting that 230 volt AC to 5 volt. And if you just zoom in over there, this is written HLK5M05. This is a 5 volt DC 5 watts module. Now, when you're going to buy this equipment, of course, 5 volt DC 5 watts, you are actually going to have this one available in 5 watts also, and it is also available in another variant which is called the HLK5PM05. Now you can see this is a very small module as compared to this one. This one is a 5 watt 5 volt module. This one is a 3 watt 5 volt module. Now in our case, since they are going to be just 5 devices, any one of them can occur. Now I guess the price difference in both of them is not more than like 100 or 120 rupees, but if you can go on with the smaller module, please go ahead with that. I guess this is available. I have given the link for buying that one from Hall Road and anywhere. The link is also available. So if you are using this 3 watt 5 watt module, certainly this means that your size will be small, and I guess this is easily available as well. So 3 watts still can do the work. So this means that you are going to, first of all, your input is going to be a AC live ground, a block connector. Certainly you have to give the live and the neutral point over there. Then there are two other elements over there. This is a varistor and a capacitor. Now I'm leaving this question open over here for the students. These two components may not be very necessary, but they are for the safety of the equipment over here. As you can see over there, you can see a capacitor. Certainly this capacitor, very small value, 0.1 microfarad, 275 volts, and then there is the varistor. Varistor, if you can search it out on Google or anywhere, maybe you will understand a varistor is something like a fuse over there, and this will take into consideration that if the voltage goes beyond this 220 or 230 volts, this will actually work as a fuse, which is actually in parallel, or in other words, this is actually going to work as a transient voltage surge suppressor. Now this may be a heavy term at present, so just take this something as a device which will actually take the extra amount of current if the voltage is high and save the circuitry which is over here, the module. As you can see, the module has the live, the neutral, and the positive and the negative. Please be very important to ensure that this is the positive and negative. But over here in the top view, for any module, either you are using 5M05 or PM05, positive is below, negative is on the top. I've just made it over here as positive on the top and negative just for the diagram, because always positive we keep it on the top side over there. So when you have this output over there, there is a capacitor over there, and that capacitor is 100 UF SMD silver. Again, you have to find out the the footprint of this component. So I am leaving 3 components in this whole PCB for which the footprint is not being provided. You have to find out the footprint of these two and this one. So this is very simple. I guess snap EDA, again the hint is the very same, and then you have the same SMD 1206 100 nanofarad. So this is very simple, 1206. This one is a little different, so maybe you will have to just spend like 5-7 minutes on searching the footprint over there. This is very, very important. So now you have got the 5 volt. So this 5 volt is enough. Now the problem here starts because the controller which we are actually going to use, because this is the world of Wi-Fi at present, everyone wants to have the control on its mobile or maybe on the laptop or something. So the controller which we are using is the most important one, or the very important one, ESP8266, very widely used in any device nowadays. So this ESP8266 is available in SMD over here. Now this is a controller in which the controller is somewhere in between, and there are pins coming out over there. You can see the pins are here. Now how many pins are there? If you just see it out, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22. Now this one is given in your that same folder. I have given it as this component, and the footprint has been given. So you can see the component is actually going to come over here, and its pads are exposed, so you will just do the soldering like this. On top you will do the soldering like this, you will do the soldering like this, and they are not that close that it will actually, in fact they are a little close and not close like the ULN2803 IC which you are actually going to place. So this ESP8266, if I can show you the above picture, this is something like this, and you can see this structure. This is actually that Wi-Fi antenna. So this is going to connect with your controller, that is your mobile or whatever. It's going to give that Wi-Fi signals in B or I guess a G range, not the N range over there. And it is going to actually have the backside something like this. You can see, because this is the flipped side, so the reset button, the ADC button, the enable button, and these are some pins which are actually going to control, and of course the VCC and the ground. Now this controller, which is actually the Wi-Fi access point, is called as ESP8266 and 12E, but this works at 3.3 volt. The problem is this. So this is working. Now remember, you will understand this in your future classes, that your voltages, the controllers, they lesser the voltage, the less power they are consuming. So technically you have less amount of power being consumed. So that's why nowadays modern controllers, they are not operating at 5 volt. You will still find out Arduino or any other one still operating at 5 volt, but the voltage is moving on to now even 1.8 volts. So the microprocessor in your laptops or your mobiles or something, they even are working at 1.8 volts in some cases. So this 3.3 volt is going to be generated by a small module, that is a small regulator, which is very commonly available, maybe like 4 or 5 rupees, I guess. The cost AMS1117 3.3 volt, which means that this is a AMS1117. The pin shape is something like this, and it's almost just like a transistor that you have actually shown soldered up till now in any experiments. This one is ground, this one is output, this one is input over there. You just have to put it, easily found out in your LTM library, SOT223 packaging. This is the input, so this means this pin will be connected here. This pin is ground, so this will be connected here, and the output, that will be actually having that 3.3 volt. So this 3.3 volt will be available for the IC, and very, very importantly, do not miss these two capacitors in tantalum. This is very important. They are tantalum capacitors, not normal capacitors. Tantalum capacitors are a type of capacitors which have very low effective series resistance, ESR, so that the capacitors can behave near to ideal behavior. This one is a 10 microfarad. Of course, the voltage is not going to be more than 10 or 15 volts because we are working at 3.3 volt. Here it's also just simple 5 volts input. So the 5 volts which we generated over there, this is going to go in this regulator, and this 10 microfarad tantalum SMD again is going to be at the input. This is going to be at the output, and this 3.3 volt which you are actually going to generate will be available at this ESP8266. So this means, very, very importantly, one thing maybe which I have missed over there up till now, this one is also 3.3 volt. So when you are going to place the ESP8266 SMD version, you are going to give your 3.3 volt here, which is actually this pin over there from the top over there. The pin configuration is already shown in this one, or you can see on that one. And then you have the enable. This enable is very, very important. You have to give 3.3 volts at this pin. Now when you have given this output, it will be, now whenever you want to program this microcontroller, now this has very small pins, so you have to program it by some serial transmitted data. That serial transmit data is actually going to be available. So you are going to put a 2-pin male header somewhere, and this is going to be the receiving pin, this is going to be the transmitting pin. So this is these 2 pins and this pin over there, they are actually used for the programming of this one, because you have to tell this controller first of all, okay, connect with that Wi-Fi, or the password is this, so that code. Now I'm not going to go in that deep detail. Those who will actually make this PCB and run it, as promised, I will share the code for this one, or even in fact you can come in Maker's Lab and I can code it from these 4 pins. But you have to connect this one on your PCB. This 2 pins connected to this 2-pin male header. this connected, this is the flash pin, and whenever flash is being used, this means that I am going to flash or program this ESP8266 over there. So this has to be connected, and the other second pin has to be ground over there. This is very important. So these two pin male headers, which makes it 4, and then just like any other circuitry, this is a reset circuitry. As you can see, this is that reset connected with our resistor and a capacitor, and then the upper part is connected with 3.3 volt and an SMD resistor, SMD capacitor, and the center pin of this one connected to the reset pin, and then the other one connected to a male header, the second pin connected to ground. Remember, these two should be a 2 pin here, a 2 pin here, a 2 pin here, 2 pin here, 2 pin here. These 6 pins are of as such no use for the circuitry, but we will use them so that I am going to program this ESP8266 so that it can accept that Wi-Fi password or whatever. And then the very important thing, that you are actually going to connect your circuit, which is actually the transistor, to these 5 pins over here, which I have named them. Now, why they are fixed over there? Because these 5 pins are available for controlling the data, so that when you are going to press some button on your mobile, maybe it will be a website over there. So as soon as that will be pressed in the code, it will make this pin GPIO 5 3.3 volt, and that 3.3 volt is going to come and connect it with this one. Now I'm putting a male header also there, so that sometimes you want to externally control it during debugging or whatever. So this 5 pin male header. So this means 5 of these circuitries of transistors, and these are the pins which you have to connect it. Now the track size for this one has to be the same track size which is actually coming out of this ESP8266. So the current is not that important over here. Yes, the current is going to be important for the load. I will just talk on that a little later. So this one is the ESP8266. Just one controller over there. 5 pins will be originating wherever they are. GPIO 5 will be coming here. GPIO 4 will be coming here. GPIO 14, wherever it is will be coming here. GPIO 12 will be coming here, and GPIO 13. So these 5 pins will be connected to, of course, with a male header in between, connected to 5 of these transistors. Very small transistor, you already know. This is 2n3904 or MMBT3904, having 1A on the top written over there, and this will be the DC ground connected over there. Do not miss this 10K bleeder resistor, which is very important, and also do not miss this diode. This diode is actually the lifeline of your transistor. If you do not put this diode, the inductor is going to produce so high LDI by dt that this is going to be damaged over there. This is going to be an NPN transistor, and this will be working over there. Now this relay over there, which we are going to actually connect, this one over here totally, excluding actually the diode. This one has how many pins? 1 and a 2 and a 3 and a 4 and a 5. So those 5 pins are in the footprint of the transistor. Now, the relay over here, sorry about that. The relay is something like this. You can see this is a yellow shaped relay, and you can count the number of pins here. 1, 2, 3, 4, 5, 6. So 6 pins are there. Now we needed 5 pins over there. So the footprint given to you has everything written over there. Now you can see over there, these 2 pins are common, and I am seeing on top over there. This is the top placement. So this relay has to be soldered on the bottom layer. This is very important. So these are the common pins, and that common pins, I mean the common pin over here at this point, which you are going to connect with AC live over there. So this means that these 2 are the common pins. This one is the normally closed pin, this one is the normally open. And since I have told you that you have to connect it to your normally open pins, so each transistor normally closed, you are not going to connect anything. Both of these are the common pins, so this means both of them you can put a simple fill area over there, and you can have that connected to your AC live, and then that AC live is going to internally, the fulcrums are going to switch or whatever, and this will be connected to your normally open when your coil is going to be energized. So this is that coil A and coil B. This is not actually just the entering terminals, and by entering terminals I mean this is that entering terminal of coil A, leaving terminal of coil B, and then it will be entering inside, and then from there it will be having a transistor. So it's very simple circuitry, nothing NC over there. Now this pin, the wire size which is going inside this coil A, coming out of coil B, it can be of the same size because it's very small current, not more than 100 milliampere. So it can be easily done. But yes, the fill area region will come. for the pins where you have the AC live connected to the common pins, and then from here connected to the block connector for all the 5 relays over there. They have to be a thick fill area. Remember, you're going to employ this device for controlling the relays of maybe 5 fans, 5 lights or something. So the fill area should be capable of withstanding at least 1 ampere of current, because if you are having a fan over there, at least it will take something 0.6 or 0.7 ampere. If you have like something 2 fans on that relay, so it will be something 1 ampere plus. So please kindly make this pin from AC live to the common pin of each relay. That has to be at least, I would say, 1 mm at least. 1 mm is the minimum, but I would like it if it is something 1.2 or 1.4. And then from here to all of these block connectors. Now this block connector will be having 5 over there. Now this 5 will be the connection points of your devices on which you are going to give that 220 or 230 volts over there, shifted from the relay. So relays are actually going to put that. Now this AC live I have not indicated anywhere. For this AC live, you can put a 2-pin block connector or a single pin block connector over here like this. I will share the footprint with you later on. So this AC live is actually going to be the pin over here, and that AC live is going to give the current to the other parts over there. And one thing very, very important, if you are making it a 2-layer PCB, which of course I would like it, everyone should make a 2-layer PCB with power module, relays, male headers and barrier connector. Now what is a barrier connector? As you can see over there, whenever the wire is going to be inside it, there is a big barrier over there. You can see the barrier between each pins over there, and this barrier is also evident in the footprint of this one. So those who have seen the footprint over there, I talked about this one. These were the 2 modules. Better if you use the 3-watt module so that the size is small. This is that barrier block connector, 1, 2, 3, 4, 5, and this is going to be a big size. So please try it that your PCB has this barrier block connector on the edge of the PCB, because you don't want the 230 volt lines directly inside of the center of the PCB. So this is that barrier block connector over there. This is that Esp8266 AMS 1117 3.3 volt regulator. The relay, that is HLK 400F 5 volts. You can see I told you this one was a common, this one was coil A, coil B, and normally open, normally closed as depicted in your circuit diagram. You already are familiar with 2n3904 sMD, which is coming in SOT 23 packaging, and then this is the diode already shared with you, and this diode is again sMD, which will be coming in parallel to the relay. Now very important point, just like any other PCB you have designed, the relay, the barrier block connectors, the male headers, the block connector 2-pin which is over there, and the HLK PM05 over here has to be placed on the top layer, soldered only on the bottom layer. Why is that so? Because if I show you all these devices over there, if you see this device, this can only be soldered on 1 layer. This can be only soldered on 1 layer. And secondly, these 2 devices, when they can only be soldered on 1 layer with the addition of the male headers or whatever, or the block connectors which you are using, so they has to be placed on the top layer, because you want your PCB to be accessed from the top, so that the barrier block connector, in these 5 connectors, you are going to put that wires over there, which are actually coming from 1 fan, 1 relay or whatever. And then there 3.3 volt or 5 volts are being generated in this PCB, and this is going to be turning on those 5 devices. Remember, for AC live, I have still not given any over there. It will be better if you can use a 5-pin block 2-pin block connector. Why 2 over there? Because 2 pins normally does not come in 1 pin. So I will share the footprint of a 2-pin barrier block connector, the same 2-pin, and you can use it for AC live. Remember, this AC live is exactly the same as this AC live over there, but remember, put a block connector over there, because this is actually the power supply of this one. So practically this AC live and this AC live, they both are the same thing. So be very, very careful that you do not mix. And one thing very, very important, the AC ground and the circuit ground, they both are totally different things. Where is the circuit ground being used over there? The circuit ground is this ground, this ground, this ground over there, this ground over there, or this ground over there, or this ground over there. This is completely different from the AC ground, which is this line coming inside the module. So this is just going in the module, coming from the block connector, and then it is not available in any of the area. Remember, this is not available in any of the area, so they are completely different. There are two power voltages. One is the 5 volt being generated from this black color module, and the other one is a 3.3 volt being produced by AMS 1117, available in SOT 223 packaging. And then you have the barrier block connector. Please make this possible, that 5-pin male headers for control of 5 devices if externally controlled, and a 5-pin barrier block connector, preferably at the edge of PCB. Why I am saying that? Because if you are going to make a small PCB supposedly, and that PCB is something like this over there, so on the PCB the barrier block connector is somewhat here like this. So this is 1 2 3 4 5, so this is 1 2 3 4 5 barrier block connector. The male header can come over here, and so it's easily accessible. Now the size of the PCB, let me talk on that point, which is very, very important. It should be somewhat, I have written a value over here as well, you can see that value. It has to be something in 90 cross 40. This is the maximum limit. It will be smaller, much better. But remember, adhere to these rules, which are that the 5 relays, the barrier block connector, the male headers, the block connector, which is when the AC live and the ground, and the power module, which is actually the HLK PM05, they have to be placed on the top layer. You can place ESP8266 on the bottom layer or the top layer, totally up to you, wherever you feel easy. You can have vias or whatever. The only fill area that I require, or I something, is this, that the point where this is going to be connected with this common over there, this one over there, and then this normally open contact coming into the barrier block connector. I'm using the word BBC over here, that is for the barrier block connector. So this is going to be just one block, and as you can see, this is going to be, the footprint has been given to you. The only footprint which I guess I have not given up till now, I will share maybe with your CR just after this video, is the AC live, which has to be provided from a 2-pin barrier block connector over there, and it will be again a 2-pin something. The reason of 2 pins is this, because it does not come in single pin over there, and these are high current connectors. I could have used this block connector over here as well, but they are not capable of handling that 0.6 or 1 ampere continuously. This is very important, because the devices, when they are turning on and they are turned on, they will be turned on for maybe like 1 hour, 2 hour, 3 hour, maybe for 12 hours. So this is very important that in this PCB, just take care that this fill area from the block connectors, or barrier block connectors, to the normally open pin and the AC live connector coming into the common pin of that relay, they are fill areas, and at least 1 to 1.2 mm, so that it can handle the current over there. And this is all experiment number 11A, and I hope you can still do it very easily. As you can see, the circuit diagram is there, and I have shared with you how this is working. Do not miss the relay part over there. And very importantly, these are some of the major new components. I guess the resistors and the other things we are already familiar. If you want to use 5M05, if you want to use PM05, it's totally up to you. Not that much difference, but if you are very concise on the PCB design part, and this is the relay signal over there, and then these are the sMD components. So try to make it as small as possible, and I will make sure that if the top 2 who have the smallest and the most sleek design, I will be making their PCB myself over there, or maybe I can order it and I will pay the expenses for those 2 PCBs. So 11A students, those who are doing it, so just try to do it as smallest as possible, and the ESP8266 is the Wi-Fi access point which is being controlling the total overall. Please try to submit it by tomorrow. Hopefully I will give a deadline by tomorrow, 23:59. That will be 22nd June over there.